So, welcome, dear friends. In our previous discussion, we have explored some of the case studies in which we were going for the primary, secondary, tertiary recycling, specifically through the 3D printing route. So, like in our previous discussion, we came to know that primary recycling without blending, secondary recycling, mechanical means with blending, tertiary recycling, chemical waste, blending, quaternary recycling, energy recovery. So, in our country, most of the work is being done on the primary and secondary recycling as this is the cost effective in nature. So now we will see some of the example of the secondary recycling using ABS and through 3D printing with a enhanced 4D application, which can of course be used for the different exotic structure and it will be having some sensing capabilities. So what I have planned is the example for the secondary recycling of ABS, in which the graphene has been reinforced. As we know that ABS is insulator and graphene is basically the one of the best conductor, and how it will be affecting the rheological properties, thermal properties, magnetic properties, and of course the mechanical analysis. That is the point of our discussion. So what actually we did is we selected the ABS and then by adding the different proportion of the graphene like 0%, 2.55, 7.5, we try to ascertain the MFI. So as you can see, initially as I am increasing the graphene proportion, so MFI is increasing, right? But after certain value, let us say limit of 10% graphene reinforcement of a particular grain size, right? Then it start decreasing, and we try to ascertain that why this is basically happening. Now to understand this, we have to go for the FTIR analysis, and in which we will be talking about the bond stretching, how they are basically affecting the type of the bond formation, bond characteristics, how they are actually varying. That we will see in the case studies. At this moment, let us take it like higher proportion maximum that is possible, that will be good for me. But most of the commercial printers, they allow the flow of the material from 2 to 3 gram per 10 minutes, specifically for 3D printing application. So we try to see the again the thermal property, how it is affecting again the TM, that is melting, and then glass transition, then the crystallinity behavior, and the enthalpy. So what we observed, as I am increasing the graphene proportion, the heat capacity which is represented in joule per gram is basically increasing. That is of course it has to be, because the graphene is definitely the one of the best conductor. So we try to see what is the effect of graphene reinforcement on corrosivity, on retentivity, on magnetization. And as I am increasing the different proportion of the graphene, so there is a significant effect on corrosivity, retentivity, and magnetization. So depending upon the period for which I need to magnetize the material, I can think of adding these type of reinforcement, and I can tune the level of the reinforcement. So what the basic idea is, like for this particular example, the 10% reinforcement was selected to be one of the optimum for the period selected based upon the retentivity and the corrosivity. So one can customize this by simply just reinforcing and making the filament and then firing on the system. We can actually use this for a smart 4D behavior, right? So continuing with this, to enhance the same knowledge, we tried to explore the same behavior with a piezo material. In a typical piezoelectric material, if I apply a load, there is a change in length. If I release a load, there is a it comes to the original position. So we came across a material known as PVDF, which is polyvinyl difluorine. It is one of the piezo material. If you just see the chemical formula for this PVDF, what we observe that there is a carbon-carbon chain, and alternative there is a hydrogen and fluorine. Now, if I apply a load all the hydrogens are aligned to the one side of the carbon chain and all the fluorine into the other side of carbon chain, right? We call it as the beta phase. Now once this is the case of like BPDF is in the beta phase, it represents a good condition for contraction and expansion, right? Otherwise, once I release the load, it comes back to the alpha phase, in which hydrogen and fluorine are the alternative elements over there. So what we can do is, by doing the load application, which is analogous to the voltage in electrical, I can basically shift the material from alpha to beta and beta to alpha. Now, what we came to know from the literature only, that barium titanate as a reinforcement helped me in increasing the beta phase in PVDF and in increasing the piezo behavior. And then with the graphene reinforcement, basically we can basically enhance the conducting behavior. So this has been done to get the 4D application. So how we proceeded in this, like we selected initially the PVDF 98%, and in which the graphene was selected as 2%. So we call it as a this proportion as X. So in this we added Y, which is basically the barium titanate. So this proportion X with 90%, 85%, 80%, we tried with the different proportion of graphene and try to investigate the MFI values. And then a DOE was planned, and using the different conditions like temperature, RPM, and the composition like ABC, we try to develop the filament, and we observed their mechanical properties in terms of peak strength, break strength, modulus of toughness, and try to see their stress strain curve. Then in a typical application, so we did the ANOVA analysis and find the best setting. Then performing the DSC, like in the previous case I have already explained, we are interested in their glass transition, we are interested in their melting temperature, we are interested in their crystallinity and the enthalpy. So we came to know which one is the better, and finally a disk has been printed, and for this disk is its D33 parameters were observed, and we got very good D33 values ranging up to 50 picocoulomb per Newton, so which is good enough for getting any sensing application. So this is the live actual 3D printing you can see over here, and these discs have been printed by a in-house prepared filament. So this help us in developing in-house sensing material for n number of applications, right? So that can be done. Now extending this study further, we use similarly a ZNO nanoparticles into the PLA thermoplastic materials. PLA sometimes under specific condition also shows the piezo behavior and the shape memory feature. So that has been improved by reinforcement of ZNO. Then basically the interest is the tuning of thermal, mechanical, morphological and the shape memory features. So you can see over here the mechanical blending of ZNO particles. Here you see this is under the category of secondary recycling, because I am adding the material which is a ZNO in the form of nanoparticles, putting it to the machine and making a filament. So these type of filaments were prepared, and then doing the DSC analysis, so we can clearly see the comparison of virgin PLA granules, and of course when I am doing the ZNO nanoparticles reinforcement, what is the variation in the TG, what is the variation in the melting, then crystallinity, right? And then we try to explore this with the reinforcement of 1% ZNO, 2% ZNO, how my thermal behavior is changing. Now this is really interesting to see. What we did is we took a PLA virgin material and print a component like U, right? So we put it into water for some time, and what we observed, this there is an extension of U, it becomes V. Now this is a deformation. Now what we want, that it should come back to the original position. So we try with the different stimulus and how its shape recovery take place. Like in this case, when it was put at the room temperature for 25 degrees Celsius for let us say good number of hours, let us say 5 hours. So there is a change in the shape. Now when I put it into the another environment, so there is a recovery coming back to the original situation. Now once I put the reinforcement of ZNO, the recovery was quite high, right? So this can be, a good sensory material, means the you after deformation again coming back to the original position. I have seen couple of papers in which people have reported they used a wire filament, and they put some strain, right, and then they put that filament into the water with some stimulus as a temperature, then the again the length contracts. This is basically I can use it as a stimulus to have a 4D behavior. So similarly the tunability is possible. So we try to observe what happens at some low temperature 10 degree and what happens at high temperature. So in cases when I am near to the glass transition, and of course sometime near to the recrystallization, basically the shape recovery is observed as the highest one. So accordingly, what happens to the material when I am playing with the different stimulus condition, we try to see its morphology, and we try to see the effect of the porosity on it. So what we observed near to the TG, if I play with my material, the chances of the recovery are observed to be highest. So in this way we can tune our material for the mechanical properties, and can have a development of good in-house sensor, which can finally help me in developing an auxetic structure with a 4D behavior. And finally this will be used for the digital twinning at any mechanical, manufacturing, biomedical application where I need to take a signal in the form of some sense, right? So that can be the advantage of these type of the smart materials. I hope you enjoyed this session, and this is really useful to all of you. At the end, just I want to summarize. We can basically customize the mechanical, thermal, morphological, sensory properties through reinforcement and through auxetic structures. And what I have to do is do some series of experimentation for establishing the property of my material. I hope this is useful to all of you. In our next session, we will see about the 3D printing, specifically all these protocols for the polymer materials, and how to develop our own material for different engineering application. Thank you very much.